5 finished ladder diagrams, lined up, solved, and running. These are 5 classic ladder logic diagram examples. And by the end of this video, you will have solved every one from scratch. A motor latch, a forward-reverse interlock, a timer, a counter, and a lamp that blinks itself forever. Each one teaches a new trick. We state the problem, build the rung live, read it as a sentence, then watch it energize. Let's solve all 5. Quick ground rules before we start. Every rung reads left to right, powered only when all its conditions are true. If drawing rungs is new to you, watch the How to Draw episode first. If reading them trips you up, the How to Read episode is the one you want. Both are linked below. Here, we assume you can read a rung, and we spend our time solving real problems. 5 patterns, 5 new ideas, a latch, an interlock, a timer, a counter, and an oscillator. One thing worth doing right now. Every diagram in this video, you can build free in your browser at CircuitDiagramMaker.app. No install, no sign up. Open in a tab and solve along with me. Example 1, the motor latch. The problem, 1 press of start should run a motor and keep it running. 1 press of stop should kill it. Here is the rung. A normally open start contact, then a normally closed stop contact, then the motor coil on the right. Press start now. Power flows, the motor energizes. But release the button and it drops out. Nobody holds a button, all shift. The fix is the seal-in. We branch a normally open motor contact around start, the output feeding back on itself. Press start once. The motor latches on, the seal-in closes, and now the branch holds a rung. Release start, and it stays running. Press stop, the rung breaks, and everything drops. Read it as a sentence. If start, or the motor is already running, and not stop, then run the motor. And notice stop is normally closed on purpose. If that wire ever breaks, the rung loses power and the motor fails safe. That single choice is why real machines use it. 1 rung, 3 elements, and a feedback branch. That is the most common rung in the world. You will find this exact rung behind almost every motor, pump, and conveyor on a plant floor. Learn it once, and you start to recognize it everywhere. Example 2, the forward-reverse interlock. The problem, a motor that runs both ways, forward and reverse. But if both contactors close at once, you short the supply and something burns. So we need a rule the wiring itself enforces. Never both directions together. Rung 1 runs the motor forward. A forward button, a stop, and the forward coil. Rung 2 is the mirror, a reverse button, a stop, and the reverse coil. Now the interlock. On the forward rung, we had a normally closed reverse contact. On the reverse rung, a normally closed forward contact. Each direction blocks the other. Watch. Press forward. The forward coil energizes, and its contact opens the reverse rung. Now press reverse. Nothing. The forward coil is holding the reverse direction locked out. Drop forward, then press reverse, and the motor swings the other way, locking out forward. Read the forward rung. If forward is pressed and not stopped, and not already running in reverse, then run forward. That cross-wiring is an interlock, and you will see it anywhere 2 outputs must never fire together. Dampers, valves, hydraulic rams. 2 rungs that police each other. No timing, no controller trickery, just 2 normally closed contacts. Good designs back this up with a mechanical interlock too, so the contactors physically block each other. But this ladder interlock is your first line of defense. Example 3, the on-delay timer. The problem, when someone presses start, the motor should wait 5 seconds, then run. A warning buzzer sounds in that gap, so nobody is caught by surprise. Enter the timer. This block is a TON, a timer, on delay. It has 3 things to know. An input that starts it, a preset, here, 5 seconds, and a done bit that turns on when the time is up. Rung 1. A start contact drives the timer's input. The moment start is held, the timer starts counting up toward its preset. Watch the accumulated value climb. 1, 2, 3, 4, 5. The instant it reaches the preset, the timer's done bit snaps on. Rung 2 uses that done bit. A normally open contact, named for the timer, drives the motor coil. So the motor only runs after the timer finishes. Read it. If start has been held for 5 seconds, then run the motor. Let go of start before the 5 seconds, and the timer resets to 0. It only completes if the input stays true the whole time. One more detail. The accumulated value is stored as a number, so you can show a live countdown to the operator. Many panels display exactly this timer. On-delay timers are everywhere. Start delta starts, pump lead lags, conveyor warnings. The pattern never changes. An input, a preset, a done bit. Example 4, the up counter. The problem, pack 12 bottles into a box, then push the full box down the line and start again. We need to count events, not time them. That is a counter. This block is a seat EU, a count up counter. It also has 3 parts. A count input that pulses it, a preset 12, and a done bit when the count reaches that preset. Rung 1. A sensor contact feeds the counter's count up input. Every time a bottle breaks the beam, the count climbs by 1. Watch the accumulated count. 1, 2, 3. Each bottle adds a pulse. Notice it only counts the rising edge, the moment the sensor goes from off to on, not while it stays blocked. At 12, the done bit turns on. Rung 2 uses it to fire the eject output and push the box away. Read it. If 12 bottles have been counted, then eject the box. And every counter needs a reset. A reset button, or the eject itself, clears the count back to 0, so the next box starts fresh. And counters can remember their value through a power cycle if you make them retentive. That is how a machine resumes mid-batch after a stop. Counters run your world. Parts per pallet, cycles before maintenance, people through a turnstile. Count the pulses, act on the total, reset, repeat. Example 5, the flasher. The problem, a warning lamp that blinks on and off, on its own, forever. No button held, no operator. Just a steady blink. This is where timing feeds back on itself. We use one timer, and we wire its own done bit to reset it. The timer counts up to, say, 1 second. The moment its done bit turns on, that same bit, as a normally closed contact, breaks the timer's own input. The timer resets. Its input closes again, and it starts counting all over. The result is a done bit that pulses on, off, a clock ticking away inside the PLC. Now hang a lamp on it. A contact from the timer drives the lamp coil, and the lamp blinks in time with the pulse. Watch it run. On, off, on, off. Nobody is touching anything. The rung is oscillating by itself. Read it. If the timer is not done, let it count, and when it finishes, reset and flash the lamp. Change the preset and you change the blink rate. A half-second preset gives a fast strobe. 5 seconds gives a slow, calm pulse. 2 timers give you independent on and off times. A long dark, a short flash. This one pattern drives every blinking beacon on a machine. Let us prove one of these is real in a free editor. This is CircuitDiagramMaker.app with a DOL motor starter template open. It is the hardwired cousin of example 1, a control supply, a breaker, the stop button, the contactor coil, and a thermal overload. Click any part, and it is a real component with a label and a value. That contactor coil is K1. Now hit Simulate, run the DC analysis, and real numbers land on the wires. 24 volts from the control supply, with the running lamp's current shown right on the diagram. The energized path lights up, exactly the seal and logic from example 1. One honest note, this editor draws and simulates control circuits beautifully. But to execute a ladder program scan by scan, inputs, logic, outputs, over and over, you want a PLC simulator. Our sister tool at plcsimulationsoftware.com runs the full timers and counters you just saw. Both belong in your toolkit. Draw and prove the wiring here. Run the ladder logic there. And notice the pattern. Every example was just contacts, coils, and 2 blocks. Master those, and the biggest programs are only more of the same. So there are your 5 ladder logic diagram examples solved. A latch, to hold an output on with a seal in. An interlock, so 2 outputs never fire together. A timer, to act after a delay. A counter, to act after a number of events. And an oscillator, to blink forever on its own. Master those 5 patterns, and you can